right, good morning, everyone. I'm thankful to be able to present this remotely, and I really appreciate the talks this morning for really setting the stage for what I'm going to present. And so I'm going to tell you a bit about what we know about the structural evolution of galaxies in the early universe. So the work I'm going to present comes from two surveys, from Sears and from Cosmos Webb. And so these are the two surveys that I've really spent most of my life, working on these last couple of years. Have taken a lot of my time. And I don't need to give a big overview because I think people are already familiar and have already discussed these surveys a bit. But what I did want to highlight is that both of these surveys have made public data releases, and I've highlighted the web pages here where you can go and download the data. Sears is complete, so all of the data, imaging, and spectroscopy are publicly available and reduced and calibrated, so you can download those data. And Cosmos Webb, we've half of the data is now available here. Our remaining observations will be taken hopefully very soon. And then I also want to highlight the publications below. So Sears has two papers highlighting the NIRCam and MIRI data reduction and data sets. And we have an overview paper for Cosmos Webb. So just wanted to make a quick advertisement about those before moving on. But today, my goal is to tell you a story about what we've learned about structure of galaxies in the early universe from the early days of JWST data. And for a little bit of context, right, it was nearly 100 years ago that Edwin Hubble first put together what we now know as the Hubble tuning fork diagram, which you can see here on the left in this image in the nearby universe. And so what he found was that galaxies nearby tend to have disk-like structures with spiral arms and bars, or they tend to have elliptical-like structures. And then a handful of galaxies are irregular. And that picture has really held as we've looked at galaxies at higher and higher redshift. With the Hubble Space Telescope, we've been able to probe rest frame optical galaxy morphologies out to nearly a redshift of 3. And we found that some of these same basic structures were in place. That is, galaxies tended to be disk-like or they tended to be spheroid-like. Even though in detail their morphologies are different, right? They tend to be smaller, they tend to be messier and clumpier as they are growing. And so with JWST, we can push even further back, right, past this 11 billion years in order to see what galaxies were like at even earlier times. Because it allows us to probe the rest frame optical light to even greater distances, but also see far fainter structures than we've been able to see before. And so we'd like to understand galaxies at these earlier times in order to see when structures like disks, spiral arms, or bulges were actually first able to form, right? We want to understand when that Hubble sequence was actually first put into place, right? Where those building blocks came from. We'd like to understand what galaxies were like at even earlier times than Hubble was able to probe in order to understand when the Hubble sequence was first put into place. And I'm especially interested in studying the role of galaxy mergers in driving this morphological transformation, but also in impacting galaxy evolution in general. So once the first images came out a couple summers ago, this was one of the first things that I think a lot of people were excited to know about. And of course, we also all wanted to know about, the highest redshift galaxies we could find, and we heard a lot about that. But I think we also wanted to know, what did these galaxies actually look like? And so we conducted a first study using the early imaging from the Sears field, right? So Sears is one of the early release science programs that had data taken early, in June of 2022. And so since this field was extensively studied by Hubble, we could conduct a direct comparison between the galaxies we observed here with JWST and Hubble imaging. And so this image here just shows the mosaic of those initial Sears pointing. And then highlighted here is just a sample of some of the galaxies that we selected out at high redshift. And so these are redshifts greater than 3, kind of a range between 3 to 6. I'm just highlighting, the general diversity of morphologies we see in some of these galaxies. And so we analyzed their morphologies in a number of ways. First, we looked at them visually and classified their structures, but we also looked at them quantitatively. And so it's a bit of a comparison. We compared what we found with JWST with earlier morphology measurements from candles. So the plot here shows the fraction of galaxies of different morphological types as a function of redshift as we knew pre-JWST. So this is based on imaging from Hubble in the Candle survey. And just for simplicity here, I've highlighted galaxies that have disks here in cyan, galaxies with spheroids in magenta, and galaxies with irregular features in this maroon color. And these are intentionally not mutually exclusive because galaxies can have multiple properties. And so to briefly summarize, the fractions here for disks are roughly 40%, up until about redshift 5, and then drop off quite dramatically. And the other morphologies drop off pretty dramatically as well. And that drop off is really driven by the fact of this bottom plot that shows that with Hubble at these high redshifts, most of the galaxies were either unclassifiable because they're just really tiny, really faint, and hard to see any structures, or completely unresolved, right? They were just point sources in the images. And so then when we look at galaxies with JWST, we see a different picture, right? The fractions of all the morphologies increase because of this plot down here, right? That shows almost none of the galaxies are now unclassifiable or unresolvable, right? We can now see all of these galaxies in great detail due to probing the rest frame optical light, but also due to the incredible sensitivity of JWST. And we see a large fraction of galaxies that have disks across all redshifts. So something like 60%, up to about a redshift of 5. And then this drops, but it only drops to about 30% or so at the highest redshifts that we can probe. Galaxies with spheroids seem to be, roughly constant over this time period, right? So a substantial fraction of galaxies already have a spheroid or a bulge component in them, even beyond redshift 7. And then we see irregular features across the board. And so some of this, difference is driven by, the difference we see, now looking at the rest frame optical. I think Stacy showed some comparisons earlier that highlighted this, but a lot of this is really driven by the increase in sensitivity. I think Anna also showed a couple of images where even at the same wavelength, right, you see substantial differences between the images taken with Hubble and taken with JWST, simply because you can now probe low surface brightness features such as disks surrounding a galaxy that might have been missed before. We also looked at the distribution of some of the quantitative morphology measures. So shown here are histograms of the Sursic index on the left, effective radius, axis ratio, and the asymmetry of galaxies for 3 different redshift bins. And the Sears distributions are shown in black, and then in comparison with some different simulations. So TNG 50 and 100, as well as the Santa Cruz semi-analytic model. And the big takeaway here is really that the distribution is similar in some ways, but different in others. So, to first order, we were a bit surprised things agreed as well as they did with the simulations, even at the higher redshifts. But what we see is that the observed galaxies have a broader distribution of Sursic index, right? They tend to have things that have larger Sursic indices than the simulations do. They also have galaxies that are smaller and more compact, and galaxies that have a smaller axis ratio. So we see these differences with the simulations. We've also looked at some different machine learning techniques for trying to understand galaxy morphologies. So this is from a paper that looked at contrastive learning, which is a self-supervised machine learning technique. This was trained using illustrious TNG mock images. And so you can see the UMAP representation space of the TNG galaxies on the image on the right in the grayscale. And then the observed galaxies are shown in colors, the observed galaxies from Sears. And so on the top, they're color-coded by their redshift, and on the bottom, they're color-coded by our visual morphologies. And again, you can see some differences in the space that these galaxies occupy relative to the full illustrious TNG set. The observed galaxies tend to be more compact and tend to be also more elongated than galaxies that are seen in TNG. And if you look at the space that these galaxies occupy, some fraction of the galaxies that are classified visually as disks occupy a similar representation space as the galaxies that are spheroids. And so some fraction of these may actually be prolate elongated ellipsoids rather than truly rotating disks. And so that was the subject, of this paper by Pandya et al., who looked specifically at, the distribution of galaxies in order to determine whether some of these could be explained by prolate ellipsoids. And so these are sort of similar to the types of galaxies I think Anna was mentioning, the sort of cigar-shaped things, where you're not quite sure if that's a disk, or visually we look at it and we're tempted to call it a disk, but it could actually be something that's more prolate. And so what Viraj did was look at the distribution and model the distribution of the axis ratios of galaxies, because a population of prolate galaxies it has an excess of very low axis ratio objects compared to a random distribution of disk galaxies. And what he found through this modeling was that a substantial fraction of galaxies, something like 50 to 80%, at these higher redshifts could be explained by intrinsically prolate systems rather than something that's inherently disky and rotation dominated. So this is interesting. I think there's a mix of things happening in the structures of these galaxies. And as Anna mentioned, right, kinematics are really crucial for trying to separate these things and see what's really happening in these early disky galaxies. We've also looked at galaxy mergers in these samples. So this shows just a subset of objects with different classifications from Sears of visually identified mergers that people have found. And so what we have done is then take some of these samples and try to identify mergers using machine learning instead. And so we're using illustrious TNG images that have Sears-like noise added to them as a training set. And so this was published by Rose et al. Last year. We're defining a merger typically as something that's within plus or minus 250 million years of the merger. There's some experimentation, but the illustrious TNG timescales aren't so fine that you can divide this up too much. When we also look at both major and minor mergers. Of course, the benefit of using the simulations to train this is that the merger history inherently, which is something we don't know for the observed galaxies. And then we're training both random forests and a convolutional neural network called DeepMerge. So just to quickly highlight a little bit about the preliminary results, what we've found is that both the random forests and DeepMerge can accurately classify up to about 60 to 70% of galaxy mergers correctly. And then it seems to hit a ceiling. And there's a trade-off. You can improve this, right? You can correctly classify more mergers, but only at the expense of incorrectly classifying non-mergers. And there's probably a few reasons for this. One is that, not everything that has a merger, in its history visually looks like a merger in its image, right? It's going to be dependent on the gas fraction. It's going to be dependent on the orbital parameters of the progenitors, et cetera. So it may be that, visually this, or morphologically, this 60 or 70% with clear signatures kind of makes sense. But there's a bit more work to do here. All right, and then the last thing I want to bring up in the last minute or so is some preliminary work with Cosmos Webb. So Cosmos Webb is now nearly complete. The remaining handful of observations are expected to be taken in April. So this is just a flavor of what's possible with a survey like Cosmos Webb. And so this is a preliminary analysis of the size-mass relation done with the first half of the survey data. And so this is about 300,000 galaxies. And so this shows the size on the y-axis as a function of stellar mass, all the way from redshift 3 up to redshift 10. And overplotted are the lines from redshift 2 from van der Waal et al. On all of the plots, and then in comparison with the fit lines to the data seen here. So you can see the evolution as you go from low redshift to high redshift and how that compares with redshift 2. Most of these, of course, are star-forming galaxies, but there's still a substantial fraction of quiescent galaxies in this sample. And if you look at the overall evolution of size with redshift, this is the preliminary relationship looks like, where the previous results from van der Waal are shown up here at low redshift. And with Cosmos Webb, we're able to continue this relationship out to very high redshifts. And we see this evolution out pretty high, and a suggestion of a potential change in slope as we go out to higher redshift. But again, this is still preliminary, so stay tuned for papers on this to come out. All right, so to summarize, we see a wide diversity of visual morphologies all the way from redshift 3 to 9, with a large fraction of galaxies that appear to have disks. But there's some evidence that some of these disks may not be true disks, but are instead prolate or elongated systems. We're identifying significant numbers of mergers visually and through machine learning techniques. And finally, a survey like Cosmos Webb is now able to enable large statistical studies of galaxy structure out to very high redshift. And so there's a lot more to come. So I'll end here and take any questions. Thank you.